member of the faculty development program, who have given the wonderful opportunity to show my research in front of such young minds like research scholar, faculty members, as well as students. My presentation mainly focusing on two-dimensional material, which similar characteristics of noble metal of platinum material. So how the two-dimensional material connecting the physics and technology in the field of water splitting for the next generation. Before entering my materials topic, as all we know, most of our energy comes from only non-renewable resources, that is fossil fuel, like coal, oil, and natural gases. However, these fossil fuels, emission of CO2 is a big threat to the human as well as the earth environment. As the recent report, the globally CO2 emission level reached in the year of 2023, 37.4 billion tons. In the flowchart shows clearly indicates China and USA are the top among two countries emitter CO2 in the rest of the other countries. So urgent requirement to find non-renewable, replace the non-renewable resources to the renewable energy resources. As per the timeline graph shows, renewable energy resources require double the amount of in the next after the 20 years. So we have to work more on the renewable energy and successful commercial level changes needed for the future generation. These are some of the already explored and implemented commercialized renewable energy resources such as solar, wind energy, hydroelectric, biomass, geothermal, and recent emerging technology of electric vehicle and hydrogen fuel. However, this kind of renewable energy implemented still incompetent to with the non-renewable resource fossil fuels. We have enormous amount of sunlight, we have enormous amount of water, still need the stabilized and commercialized product of the renewable energy. Most of the research and commercialized prototype models required to save the earth and the human lives. Why hydrogen is emerging technology? How the produced hydrogen? What are the main applications? Depends upon the production of hydrogen. It has classified the 6 different colors based upon the production. The brown and gray color hydrogen produced by the traditional method, steam reforming. Steam reforming and gasification method. The traditional method which has produces more CO2 in the atmosphere. Blue color hydrogen shows the same method, however, the produced CO2 stored in the underground of Earth. However, still escaping the CO carbon dioxide CO2 is not reliable method. Then white color hydrogen shows underground deposition of hydrogen. This is not permissible to take that hydrogen. The pink color hydrogen produced by the nuclear energy resources. Then finally, the green energy hydrogen, green hydrogen shows different method like electrolysis, photocatalytic, photoelectrochemical, thermochemical method. These are the zero emission of CO2. That's why most of the research is undergoes on this green hydrogen. Then these are the some of application: ammonia fertilizer and power generation, vehicles, metal refining, lot of application from the hydrogen. These hydrogen split from the water, successfully splitted and stored in the large amount of hydrogen. That would be the biggest solution for the fulfill our energy requirement. These are main important inventor of the water electrolysis. Not only water electrolysis, the first 1789, John Rudolph Diamond and Adrian Payet van der Strijik has been given a concept of Leyden jar. Just like a first capacitor based upon the Leyden jar experiment. 1800, Alexander Volta has been designed voltaic pipe. After a few weeks, based upon the using the voltaic pipe, that Anthony Carlsell and William Nicholson as using the voltaic pipe decomposed water into hydrogen and oxygen. Then based upon these concepts, after a decade, Charles Renard has been designed French military airships for commercialized purpose during the World War time. And earlier 1900 has been commercialized this water electrolysis concept. Almost industrially you started to using the water electrolysis concept, produced more number of 400 electrolyzers, as well as in the earlier 1920s and 30s, most of the industry using only for some hydroelectric power is the mainly focusing on ammonia fertilizer for the agriculture. However, the 1970, the oil embargo has been formed. The Western country, then Middle East country has been fought like now. Then they have again the new invention is a polymer exchange membrane. That polymer solid electrolyte used for the membrane for next generation of water splitting, water electrolysis system. These are the history and progress of water electrolysis. This classifies on the 4 stages, like initial exploration, as I told earlier, 1718 into 88. Rapid development started around 1890 to 1930. Important progress has been started around 1940s to 1985. Those are Nafion-based electrolyzer, solid oxide water electrolyzer, and PEM proton exchange membrane electrolyzer. These are the important progress that has been achieved. Then after the 21st century, the researchers are mainly focusing on replace some membrane and materials, low cost materials, the cost effective electrocatalysis, and some sunlight, renewable energy to assist how the water electrolysis. At that time, they have used direct current for the water electrolysis. However, in the over period of the time, from the sunlight to how assist the water electrolysis experiment. Then as well as some of the advanced characterization technique. At the in the earliest stage, they have developed and used. No one knows how the inside the reaction mechanism, like intrinsic activity, some redox mechanism, how the behavior is during the activity stage. There's some in situ operation techniques like in situ Raman, in situ TEM. Nowadays are growing. So far in India is not achieved that level, but in during some of the foreign countries have this kind of instrument. They well established instrument know the reaction mechanism during the activity. These are the water electrolysis mechanism. As a very simple concept, once applying electricity applying through the water, the split oxidized oxygen and hydrogen has been splitted and stored. This GIF image shows just pure water is circulating. Once the electricity applied, the water molecules oxidized through the anode side. Then cathode side is hydrogen, the reduction of hydrogen. This anode side is oxidized of oxygen. Then oxidized oxygen stored in the anode side. Then released electrons traveled through the external circuit and transported through the membrane to protons. Then really transported to protons combined with the electron formed as a hydrogen stored in the hydrogen tank. This is the simple mechanism. There are two optional reactions. One of the reaction is hydrogen reduction of hydrogen, that is a hydrogen evolution reaction. Another is oxygen evolution reaction, oxidase of oxygens. Then these are the traditional water electrolysis setup. The first initially developed alkaline electrolysis. Then after the oil embargo has been developed the polymer electrolyte membrane electrolysis. Compared to traditional electrolysis, PEM is the best one because of the higher conductivity, faster response than alkaline electrolysis, the lower ohmic losses with less crossover. See here the thick diaphragm, there is a lot of force, so the hydrogen and oxygen gases cross over, the total experimental has been spoiled, as well as the thick diaphragm has the high resistance, so the lowering the intrinsic conductivity. So compared to that one, the PEM is the best one. The nowadays recently explored the used some of the solid alkaline exchange membrane to improve the performance. These are the some of state-of-the-art catalyst for the hydrogen evolution reaction as well as the oxygen evolution reaction. Mainly, the well-established and stable performance through only noble metals such as platinum, palladium, rhodium, iridium, like this material. For oxygen, ruthenium oxide, iridium oxide, the same iron Ru. So we have to these kind of materials less amount in the air. So we have to alternative materials to equal performance like the noble metals. These are the various techniques have been already established and tried and published more papers, and some prototype model has been designed various of stages has been crossed. These are the some important technologies has been used, interface mechanism and surface mechanism like heterostructure design and defect engineering, as well as the catalyst and electrode surface and catalyst and electrolyte surface interface, how the interface is decrease the resistance and increase the electron transport, the conductivity. Then some crystallographic side like a crystal facet and surface facet. Mainly some of the researchers focus on morphologies like 0-dimensional, 1-dimensional, 2-dimensional, which one is suitable for the electron transport, and which one is created high specific surface area, and as well as the more porous, some morphology as coastal morphology has been developed and utilized. Some, however, still research is undergo. These are the some materials has been developed like carbon allotrope, amorphous carbon, diamond, graphite, graphene. These are carbon allotrope, some metal organic frameworks, MOFs and COFs, as well as some same platinum-like behavior of transition metal derivatives, early transition metals, some metal-free catalyst, as well as some alloys, transition metal derivatives like transition metal phosphide, nitride and dichalcogenides, transition metal carbides. Based upon the alloys, different combination have been tried, then still the success rate is still is lagging. So we have decided based upon our literature review as per the achievements has been already made. We have materials. As we all know, these are the important 2D materials like graphene, MXene, TMDS and borofin. Like these materials of mainly used for electrochemical water splitting. There is two kind of water splitting, water electrolysis: photoelectrochemical water electrolysis and electrochemical water electrolysis. Photoelectrochemical water electrolysis directly take energy from the sunlight. The electrochemical water electrolysis directly take energies from the direct current DC. So our group only focusing on electrochemical water electrolysis. These are the main benefits from the 2D materials like high surface area, higher conductivity, the thick surface, the more porous and high surface, the surface, some edge sides are there. These edge sides leads to the more active sites. As well as the some defects like interstitial edge defects and interstitial defects, as well as the some some of the electronic structure, tunable the electronic structure, which could happen in the 2D materials, like improving the intrinsic activity as well as increasing active sites are the most common things needed for the water electrolysis. These are the, we have selected the material, among those material, how the synthesis of 2D material. Commonly using for the nanomaterial synthesis, top-down approach and bottom-up approach. For the 2D material synthesis, most of the research focusing on bottom-up approach, because of the top-down approach is very difficult to make the high yield product. But bottom-up approach, we can produce high yield, then the time period is very limited time period, such as hydrothermal, solvothermal method, ultrasonication method, and electrodeposition. Electrodeposition, you can use the same electrochemical instrument, the anode and cathode, you can, sorry. Some ultrasonication, then the layers are inducing some sonication, the layers has been separated, as well as some scotch tape method. You can use the scotch tape and layer, you can separate the layer by layer method. These are the some important synthesis method, easy synthesis method. So any material we can use this method. Once we decide the synthesis method, then what kind of materials we need, like powder material or grown on some substrates. Why we focus on some substrates like FTO, nickel form and copper form and graphene substrate, like the metal mesh, carbon cloth, because the powder material have the easily restacking, they need some polymer binders to the stick with working electrodes, as well as the mechanical stability during the operation. There the current, once applied the current, applied the potential, there is the peel out of the material on the glassy carbon electrodes. So if you directly grow on the material on some of the substrates, like nickel mentioned, these are the nickel form or FDS, whatever substrate you used. So the strong binding within your material as well as the electrode, as well as the mechanical stability is high stability. So electron transfer compared to the powder to the on the over the substrate material is a very fast and the mass electron transfer. The bubble detachment is higher than the powder material. So we have decided to use any one of the substrate for our experiments. Then based upon our literature reviews, some deep research, so we have decided to synthesize some two-dimensional materials combined with one-dimensional material, and again two-dimensional material combined with two-dimensional material. So hierarchical structure, as well as the same at the same time we have used some delithiation to regulate the valency state in the cobalt. So these are the very simple method. As I told earlier, we have used a wet chemical approach, that is a hydrothermal method used to the substrate of carbon cloth. First, we have developed one-dimensional to two-dimensional and two-dimensional to two-dimensional. See this the experimental procedure, just first hydrothermal, then the synthesized nanosheets or nano rods, then lithiation has been same hydrothermal method used. Then after lithiation, the LiCOO2 formed. After lithiation, LiCOO2 nanosheets on nanosheets, both one dimensional and two dimensional and two dimensional and two dimensional simultaneously prepared with two different autoclaves. After annealing, the porous structure, the specific surface area has been increased. See the surface morphology. So first one-dimensional structure, then over the one-dimensional structure, the small nanosheet has been formed. After annealing, the clear nanosheet has been visibly shown. The same kind of experiment first nanosheet grown, then there is a after lithiation, the nanosheet gotten thick, more thickness compared to the after annealing. Then after annealing, there is a small nanosheets and porous has been formed clearly. We can see through the surface FSM morphology. These are the optimization process. The same image clearly shows 4 mole 160 degrees Celsius is the suitable temperature as well as the molar level of lithium hydroxide is optimized. Other morphology, you can see there is some agglomeration, there is not uniform structure, as well as the that nano that LiCO2 formed. Some places the higher dense, some places shows the substrate like a carbon cloth substrate. So we have n number of trial and error method. We finalized 160 degrees Celsius. Then is the expanded image shows lot of small teeny nanosheets formed over the nanosheets. These are the structural and functional structural analysis through the Raman analysis and XRD analysis. You can see there is not well crystallized crystallinity of this material. There is a polycrystalline material like some amorphous and crystalline material is combined. So the carbon peak around 23rd to around 26th in the range of carbon peak through the carbon cloth, not in the material peak. That carbon peak comes from the through the carbon cloth. So these are the 4 difference like before annealing, after annealing, 1D, 2D and 2D, 2D before annealing and after annealing. Compared to these things, that we have chosen the best one, the after annealing 2D and 2D for further delithiation purpose. This Raman shift confirms there is no CO3O4 in the after annealing samples. This is the byproduct. They every refer the some battery material, the CO3O4 is the formation is acceptable. These are the deep level morphology investigation and structural investigation. See, we can clearly see the how one length nanosheet has been formed over the nanosheet. Small teeny nanosheets has been formed. Then d-spacing value around 4.66 Armstrong. The HKL is 003 is in line with the XRD result. Then EDS image clearly show the uniform formation of cobalt and oxygen. Then SAED confirms the good crystalline material, that the polycrystalline material. The same applicable for the one-dimensional and one-dimensional or the two-dimensional material image. The same d-spacing and EDS confirmed. These are the material structurally confirmed. Then we have to undergoes for the delithiation purpose. Why we need delithiation? How the delithiation is performed? Just you synthesized sample, cut small samples like 1 cross 1 or 0.5 cross 0.5 centimeter square. You can cut 5 to 6 carbon cloth. The immerse in the iodine solution. Keep the for 1 week, 96 hours, 24 hours, 24 to 96 hours. Then after the 24 hours, take the sample, do the XRD and the X-phase analysis. Repeat all the characterization. Then you see the variation of there is shift between the initial bare material as well as the delithiation material. The lithium removal has been the lower side and higher side of the peak shift confirm the partial lithium has been removed from the LiCO2. Then the surface element analysis of the surface XPS survey structure confirm all element is present. Then the XPS confirms the valency state. The mixed valency state is around high valency state like CO3 plus to CO4 plus because of the lithium removal. Once surprisingly you see after lithium extraction, there is no even 96 hour samples too, there is no structural deformation. So structurally, morphologically, our material is stable material. There is still retain the morphology and elemental or the all are the same. So we have decided the stable of our material. Then after structurally confirmed, morphologically confirmed, whatever you want, you have achieved. Then next step, we are moving to the application side. These are the general traditional water electrolysis setup. There is 3 electrode setup. The first one is working electrode. The working electrode consists of your material. Whether if you grown on nickel form, then you can use directly on the working electrode. If you prepare as a powder material, you can use a classic carbon electrodes, otherwise nickel form coated on the whatever the geometric area you need, you can coat on this side, then immerse in the solution. Then reference electrode normally use AgHCl or HeHgO, mercury electrode, or some of other reference electrode also used. Then counter electrode, you must use platinum S or platinum wire, or some other counter electrodes like graphene counter electrode or some of the papers used. The water is not fully spontaneously conduct the electricity. So we have used any electrolyzers like alkaline electrolyzers or acid electrolyzers or neutral electrolysis like KOH, H2SO4. For this experiment, uh, uh, this this work we have used for KOH, the alkaline electrolysis. So we can clearly see how the bubbles has been detached from the nickel form. If bubbles not detached from the substrate, the blocking of the active site reduces the performance. You cannot store the release, cannot your material cannot able to release the proper time of the gas bubbles, that is deterioration of your total experiment, as well as the material is not good. See this video. Through this video, we can see lot of this is anode side. Lot of oxygen molecules has been released from the substrates. The substrate consists of the LiCO2 material with 72 hour of lithium extracted working electrodes. So we can conclude if the material releases more gas bubbles, that's a good catalyst. So before going to the calculation, we have decided if your material releases more gases, our material performing better than your previous materials, like whatever you can decide this kind of materials very very actively releasing the gas bubbles. They show the lot of stable. There is no any deterioration during the experiment. If you applied some potential, there is no degradation of electrodes. So we decided our material is 100% is stable material. So once we synthesized, we structurally characterized and applied we got some active results. Then what are the important parameters in water splitting? How they evaluate your performance? This is a over potential. If you get the over potential very less amount, your material is very good catalyst. Like before the calculation of the over potential, we know the geometric surface area. The geometric surface area is different than the electroactive surface area. The geometric surface area is how much area you coated your material. Like if you use the nickel form now, there is how much area of nickel form immersed in the electrolyte solution. That is the geometric area. Don't confuse it, geometric area and electrochemical active surface area. So they depends upon the geometric surface area. We have calculated the over potential. If you are doing experiment on OER, you must subtract the 1.23 volt, because the thermodynamical potential is needed for the OER reaction, because OER is the multi-step 4-electron sluggish reaction kinetic. The OER is almost effective tool for the metal air batteries and water splitting technologies. and battery application too. So these are the important parameters we have to optimize. Then another is Tafel slope. We from the Tafel slope we have to identify the reaction kinetics of the material, then electrochemical impedance spectra. These could be the important analysis tool to know the series resistance between the electrolyte and your electrode, charge tensor resistance, electrode between the your substrate. So these are the important tool. And mass activity, how much of catalyst actively participated during the activity. So normally high amount of mass activity result gives the greater activity of OER or HER. Then next, stability, as we all know, the stable material, like how long the performs without any degradation or deterioration of your current density or material. Then turnover frequency is important to this material generated oxygen molecules or hydrogen molecule per unit per catalytic active sites on the per unit time. So the calculated from the standard potential. These are the 4 parameters for after obtain the result from the electrochemical instrument. These are the parameters confirm the our material is good or partially good or bad. So the electrochemical the parameter used, the first one is LSC, linear sweep voltammetry, then Tafel slope, then chemical double layer capacitance confirmed. These are the before delithiation. Top 3 images show the before delithiation activity, OER activity and Tafel slopes. See, the among the 4 materials, the LiCOO2 nanosheets over the nanosheets after annealing sample is the recorded the best performance around 320 millivolt over potential. So it resembles with the Tafel slope. See, is a 92.8 millivolt per decade. Then the chemical double layer capacitance. So higher chemical double layer capacitance confirm the higher specific surface area. Using the chemical double layer capacitance, we can calculate electrochemical active surface area ESEA. We can calculate from the these values. So after the delithiation, we see used the bare material, then 24 hours to 96 hours, then 72 hour material perform the better samples, a better result. See the around approximately 280 millivolt over potential has been obtained. Is a resemble with our Tafel slope. The good reaction kinetics around 71.5 millivolt per decade. Then during the delithiation, 72 hours is the best sample. Why 90 to 96 hours is the poor performance? Because extraction over the period of extraction from the LiCOO2, that will increase the over potential, decrease the performance. Then finally, we have seen the stability analysis. There is no any fluctuation almost 20 hours. See the 1.52 volt, we have applied the potential, then there is no current density losses up to 20 hours. These are the after stability analysis, morphology, topographical analysis like XRD structural analysis and morphology analysis confirm the same D spacing and HKL value. There is because MS of around almost 20 hours, the small stacking is happened, but still maintain the nanosheet morphology. So the previous work mainly focused on alkaline electrolysis, but next work mainly focus on acidic electrolyte as well as the important the 2-dimensional materials layered double hydroxide to transformation to the metal organic frameworks. Why we need to the layered why we need to the transformation LDH to MOF? Because some of the papers has been already reported LDH based water electrolysis for HER and OER and universal pH based water electrolysis. Some alone MAF also performed. However, some of the results concluded there is a small specific surface area in LDH easily aggregate the layer by the, you know the layer LDH material, there is a layer by layer. So the anions and cations, the layer the inside the interstitial water molecules. So during the synthesis, they aggregate within the layers. So is a if this is aggregate, na, there is a performance normally reduce the step, that is not a stable material. As well as the alone MAF material also some of the problem. If you decide grown on the substrate, any substrate means it is not easy to grow on 2D material because the bulk material, bulk MAF has been formed, not in the nanostructure level material. So our goal is prepare LDH to first LDH, then transformation to the MAF. We believe that this transformation is the ability to capture more active sites and transfer the electron effectively. This is a very simple experiment. The same chemical approach, hydrothermal method. Use any metal precursor you want. Like our work, we have used nickel, cobalt, and nickel ferrite precursors. Then after stirring, they used some noble metal. For there is a small amount of that is doping, small amount of Ru for the surface reconstruction. Then is tightly closed on the hydrothermal for 120 degrees Celsius for 12 hours. Then after gradual cooling, then drying for the 60 degrees Celsius for 6 hours, then formed LDH structure. Then after the drying, we used transformation, simple method, just prepared material, cut 4 or 5 pieces, then immersed in the terephthalic acid solution, that is a MAF precursor. After 24 hours, you can completely transformed from LDH to MAF transfer. This is one of the many transformation method is available. This is one of the easiest method to transform LDH to MAF. These are the some higher magnification FESEM images. We can see the material has been formed higher dense, uniformly formed. You can see the conducting substrate. There is no substrate images on seen, only materials has been formed as well as the densely formed. There is not like some of the place higher form, most of the places formed, some of the places vacant. There is fully covered through the conducting substrate. This experiment we have used nickel form, not carbon cloth. See the how morphological has been transformed from once first you prepared LDH, then after doping Ru, then after transforming BDC. First CO, the first 3 images, NiCO based images, another 3 ferrite based images, see nano wave, then aggregated nano small particle, then after morphology MAF transformation, there is uniformly arranged the nanoparticles are like nano arrays. Then NiFeLDH, see the nano sheets, but once introduce the ruthenium dopant, there is an aggregation of nanoparticles. After that, you transformation is a nano flake morphology has been obtained. See the HRTM images, there is amorphous. It is not good crystalline material. Weak crystallinity has been clearly seen. Some of the places not visible fringes or lattice fringes are there. So we concluded this is mixed amorphous and crystallization behavior. Then we clearly concluded we concluded the elements all elements like NiCO oxygen and
చెయ్యరా
నేనే చేస్తాను
uniformly distributed over the materials. Then as per the structural analysis, we have characterized 2 different categories: extracted powder, then over the nickel substrate. The the three nickel peaks predominantly show the suppress the other peaks. So we clearly see in the powder material there are lot of crystalline peaks, but higher predominant thickness suppress the peaks if you conduct a analysis on the nickel form. So we decided the material as structurally confirmed. We is in line with the already reported JCPDS cards, the functional group analysis, the BDC functional group, and NCRB and NFRB like NiCO ruthenium BDC, NiFe ruthenium BDC. There is a the metal active sites is transformed and attached with the framework. This Raman analysis confirmed how the transformation has been achieved. See, NCA, around 400 to 700, there is a band vibrational stretching with NCRB and NiCO LDH. However, after transformation, they fully disappeared that peak, that band. So we concluded fully transformed. This is not partially transformed. Some of the reported works are partially transformed. This is fully transformed work. After the structural confirmation, during the application, there is two mechanism has been involved. Like if you used an acidic water oxidation, then adsorbate evolution mechanism as well as the lattice oxygen oxidation mechanism. These both mechanism concluded depends upon the crystalline behavior. If weak crystallinity with few defects, that's called AEM mechanism. The amorphous as well as the abundant oxygen vacancy tends to the lattice oxygen oxidation mechanism. So how the LOM is achieved, the surface reconstruction we have done through the RU, amorphization, we have seen the HRT images, dissolution of the metal cations. So finally, we got some OER results using the H2SO4 strong acid. We got the result around 255 millivolt for NCRB material, 247 millivolt for the NFRB materials, that is Fe based and CO based material. The reaction kinetics shows 149 for NCRB, around 175 for the NiFe ruthenium based MOF. Almost all sample is the less than 10 RCT and series resistance almost 1 to 1.5 ohm centimeter square. Then as I told earlier, the higher chemical double layer capacitance is the better catalyst. See our two materials showing compared to others. This is not much different. However, this is specific surface area is higher than other materials. The mass activity comparatively more higher than the bare like NiFe LDH, NiCO LDH, despite of some doping, the MOF conversion is good. Then stable, you see the 20 hours of stability analysis, the material performed, there is no any current density fluctuation, no there is no deterioration. So this material is transformed and converted to the MOF, the stable one. Then after stability, we have routinely done the OER, or if you are doing the HER analysis, we must perform the HER after stability. So almost same, not much bigger variation on your over potential. So these are the final conclusion. The doping, RU doping leads to the metal surface reconstruction. That is the metal leaching, the dissolution, avoid the metal leaching and dissolution, as well as the MOF conversion increase the stability because of bimetallic like Ni and CO and NiFe. So these are the important conclusion we have made through this RU the electronic tuning as well as the surface reconstruction. These are the achievements has been made. Finally, we must perform the hot test stability analysis. Still, you can see the nickel form still maintain the whole whole nickel form fully dense growth on the substrate. The structure still retain the element. You can see the elemental analysis color image mapping shows the uniform formation. There is not any disappearance of the element. So we have decided this material is stable and performed for practical applications. Then during our literature studies, just go through one of the interesting study using the magnetic field increasing the war potential. This magnetic field utilization not all the materials, metallic behavior, metallic magnetic nature of materials like nickel series and Fe series materials. Uh, During the OER activity, we can apply the magnetic field as a for almost literature used around 400 millitesla. The magnetic field applied, the bubbles detachment is getting higher. The still in-depth research is ongoing. They mentioned that paper like future paper they will discuss more about this. But we can clearly see how the more bubbles once magnetic close with the anode side. Just see the video. The second video, we can clearly see the lot of oxygen bubbles. See, once magnet comes, it increases, gradually increases. See, some interesting studies. So, so far, so far, so far I have explained what we have made and published the papers. The two paper has been published applied materials today in impact of 8 and another paper published in the ACS journal. So still more research needed in the electrochemical water splitting and whatever the water splitting, because these are the ex situ analysis. We need the in situ analysis like in situ Raman, in situ HRTEM, then assessment criteria are like our working electrodes and nanoparticles, in situ analysis, some theoretically exposed results like operando structure and activity, stability relationship, then as well as the chosen materials, which one is economic availability, the scarcity. We must choose the scarce abundant material. Those are the research still is ongoing around the world. These are my supervisors throughout my research journey. They are my pillars of my what I have achieved so far. Uh, I respectively my supervisor Professor P. Ramaswamy and my co-supervisor during my doctoral studies Dr. Muthu Sendil Pandian. He is Professor Zheng Fei Dai, who was recently professor of Xi'an Jiantong University. Initially, I was working in the dye-sensory solar cell field. When I joined as a postdoctoral fellow in the Xi'an Jiantong University, he has guided so he has changed my field solar cell to water splitting. Is one of the great scientists. He has published more number of papers in around 5 to 6 paper in natures and advanced materials, advanced functional materials like this channel. Is a good scientist from the China. And Dr. Pandikuma, senior scientist, is now working senior scientist in CSIR laboratory. Dr. Pratishwari and Dr. Shyama Lenus. These are my The students, they are currently working in Taiwan because Chiang, under the guidance of, they are working. When I was working as a postdoc in SSN College of Engineering, I have big opportunity discuss with them and collaborated with the two students, Krishnamachari and Mr. Arun Pandit. These are the Malaysia's top 4 attractions, like Twin Towers, some we know the Asia's tallest Murugan temples, some Cameroon Island beaches. We can enjoy if someone can come and enjoy the Malaysia. Malaysia is offered visa free for Indians, visa free travel for Indian. So just utilize it. These are my morphological images. Through my research journey, I have synthesized these nano one-dimensional, two-dimensional, three-dimensional materials throughout my research journey. Thank you for your kind attention. If you have any questions, please.
Okay.
Thank you.
Thank you, sir. Your presentation was both engaging and informative, and we truly appreciate the time and effort you put into sharing your expertise with us in this evolving field.
Thank you.
Yes, sir. So we have collected a few questions from our participants. Question number 1: what are the current challenges in scaling of the synthesis of 2D platinum-like materials for industrial application?
Because the whatever synthesis method we recommended, still the scalability of the yield is very, very little, as well as there is synthesized on the some of the substrate, still using some acid based electrolytes, still there is a corrosion has been happened. The mass level production is not achieved so far. Still research is ongoing. There is the peel off of material, then corrosion of the material, as well as the yield product, then blockage of active sites, as well as the some over the period of time, the two-dimensional structure has been aggregation of the two-dimensional materials. Whatever the layer, the lattice expansion is happened. So material stability is a big concern. Or the if you go the practical application, these are the things main. Still, that's why we need some in situ analysis. The how the materials changes, what is the exact time, what is the reason. So the theoretical and in situ analysis required to work on these issues.
Okay, sir. Thank you, sir. The second question: how do the electronic properties of 2D PT-like materials enhance their catalytic activity in water splitting compared to bulk materials?
Oh, because there is bulk material, specific surface area is very less compared to 2D material. If you synthesize 2D material, there is lot of pores we can see from the HRTM images. The higher porous as well as the large surface area, making the material more conductivity. So electronic conductivity is more higher than bulk material. That is the reason researches on the 2D materials, because the electronic transport is higher than the bulk material, as well as the tunable, the electronic structure only possible on the morphology. Next question, ma'am. It's not audible.
Okay. So I'll repeat, sir. What key types are needed to transition these 2D materials from experimental research to commercial scale energy applications?
Friends, remember, I didn't understand. Sorry.
Okay. So they are asking 2D materials we are preparing to experimental research, how it is going to be applied for commercial applications.
Yeah, the same. We for laboratory scale we prepared just 2x2, like whatever the small scale level. So practical scale we can growth on the same method. The industrially developed method we can already developed in 1900 itself. Some industrial water electrolysis, proton exchange membrane, like anode side, like cathode side, we can design that electrolysis, the same kind of experiment like big hydrothermal and CVD process, chemical vapor deposition method, some lithography method used to commercialized 2D materials. We can prepare. It's already explored many places for the different application, not only water electrolysis, for different application.
So we have two more questions. Will salinity of water affect the functioning?
Sorry, ma'am?
Will salinity of water affect the functioning?
Yeah, yes, ma'am.
Then one more question. How we identify 2D and 3D materials for selection of synthesis?
Yeah,
Hope
yes,
the
ma'am.
question is not.
That only we can identify through the morphological analysis. We cannot select the material before synthesis. Ma'am. There is a specific
Is the question
template,
slower?
specific precursor has been used for 2D materials and 3D materials. It's not before
Thank you, sir,
selecting.
for patiently and thoughtfully addressing the questions from our participants. Your insights and detailed responses have added great value to today's session and have certainly understanding of the topic. We truly appreciate your time and expertise. As we approach the conclusion of today's event, it's time to acknowledge the efforts and the contributions that made this program a success. To express our heartfelt gratitude, now I invite Dr. V. Annie Ratnakumari to deliver the vote of thanks.
Thank you, ma'am. So it's my honor to deliver the vote of thanks on behalf of the Department of Physics, New Prince Sri Bhavani College of Engineering and Technology. It is my privilege to deliver the vote of thanks for today's enlightening session. On behalf of the organizing committee and participants of this FTP, I extend the deepest gratitude to Dr. Vijay Kumar Karandaman for the insightful talk on two-dimensional PT-like materials, bridging physics and technology for next-gen water splitting. Your presentation offered us a fascinating glimpse and in-depth insights on how to select materials and synthesis methods for water electrolysis process, and how to synthesize 2D materials and parameters of water splitting, which surely help the participants doing literature survey and setting research methodology in this evolving field. Your work not only demonstrates the exciting potential of PD-like materials, catalysis, and energy conversion, but also exemplifies the crucial role of interdisciplinary research in solving global challenges like clean energy and water sustainability. We truly appreciate the clarity with which you communicated such a complex and evolving field. Once again, thank you, sir, for sharing your time, knowledge, and passion with us today. And a sincere thanks to all the participants who joined us today. Your presence, questions, and engagement added a great value to the session. We, the organizers, thank the MTSBCET institution leadership for their constant support in making events like this possible. Let us carry forward the knowledge and ideas we have gained today. Thank you all once again.
Thank you so much, ma'am, for those heartful words of gratitude. Your eloquent vote of thanks truly reflected the spirit of today's event and acknowledged the efforts of everyone who made it a success. We appreciate your thoughtful expression and sincerity. Before we conclude today's session, we would like to inform all the participants that tomorrow is the last day session of this faculty development program. The session will begin promptly at 9:30 a.m. We are pleased to inform you that tomorrow's session will be led by Dr. Mangal Raja Ramalingam Vishwanathan, Professor in Engineering and Sciences, Universal Autocrat, Chile, who will be speaking on the topic Material Science, a season of science and engineering. We look forward to another insightful and engaging session. We request everyone to join on time for a smooth and enriching experience. Thank you, and we look forward to your active participation tomorrow. Thank you all.
Thank you, Dr. Annie Ratanakumari Madam, who have given
Thank you, sir.
given the wonderful opportunity to show my research in front of good students. Thank you, ma'am.
Yes, sir. It's a evolving field, and definitely it's a new kind of research area. And most of the young researchers can select research methodology and how to do the literature survey, and the labs where the facilities are available. So all such things are included in your talk, sir. So we are very happy to have you today.
Thank you, ma'am.
Thank you, sir.
Bye, ma'am. Thank you, ma'am. Jai Sri Ram, ma'am. Thank you.
Okay.
Participants are requested to fill the feedback link.